Okay, so let's get started. So today I'm going to introduce our recent development of a fast Bayesian force field from the active learning workflow and how we use it to study the 2D to 3D transformation of Stanene with molecular dynamics simulation. We have put our preprint to archive so you can refer to it for more technical details. So the first question is, why do we need a machine learning force field? Let me take the Stanene as an example. Stanene is the honeycomb monolayer of tin. It has shown some really attractive properties like superconductivity for few layer Stanene and, for example, quantum spin Hall effect. And we are interested in the melting behavior of Stanene system. So to investigate this, we have to use the molecular dynamics approach, and at the same time, for the force field, we wanted to keep the first principle accuracy. So for the force source, we can definitely use the density functional theory for the calculation. The advantage of this approach is that it is usually pretty accurate, but it is also very computationally expensive. So it is usually limited to a small system size in a short time scale. In the meanwhile, there's also the empirical interatomic potential approach. Those are very fast and can run large-scale simulations, but they are usually fit in a small temperature range and are not accurate for melting process. Also, it takes a lot of time and human effort to fit. So here I want to introduce this machine learning force field approach. For example, the neural network and Gaussian process. They are data motivated, so you don't really need to make a lot of physical assumptions to the model. Also, they have high accuracy given a large number of parameters and data. And we want to note here that usually those approaches are several orders of magnitude faster than the density functional theory. So we can run very large scale simulations with the machine learning force field. And in addition, we also desire the uncertainty quantification so that we can tell how confident our model is when we make the prediction of the forces. So because of this consideration, we choose the Gaussian process regression since it can predict the forces and analytical uncertainties simultaneously. There's a recent paper from our group published on the MPJ computational materials earlier this year talking about this machine learning force field using Gaussian process regression and Bayesian active learning. And we also have the code publicly available online for the training procedure. We want to note here that to reach a good accuracy, usually a large number of data points are needed, but the computational cost in the prediction of the exact Gaussian process scales linearly with the training set size. This will definitely hinder the capability of the Gaussian process to run the large-scale simulations. So for this problem, our solution is to interpolate the Gaussian process regression with fast spline functions, and we call this work as map the Gaussian process. So we're able to map both the Gaussian process forces and variance by the interpolation. This approach has negligible loss of accuracy compared to the original GP. It also reaches a high speed since the prediction is independent of the training set size and so can do very efficient large-scale simulations. Now I'm going to briefly introduce how we train this machine learning force field for the Stanene system. The training is guided by the uncertainty predicted by our model. Basically, we use our Bayesian force field to run the molecular dynamics for the Stanene system, and in each step, we're able to predict both the forces and uncertainties for the configuration. If our model is unconfident of a configuration, we will use the density functional theory to calculate the true forces for this configuration and add them to the training set. This workflow forms a closed loop to improve our model accuracy. In addition, because of the acceleration from mapped Gaussian process, the active learning can be more efficiently done on a larger system size. so that possible finite size effect can be overcome. Therefore, we also implement the hierarchical active learning scheme to train the system with increasing system sizes. For each system size, we run the active learning for several picoseconds to nanoseconds. And finally, after a force field with converged accuracy is obtained, we can use it to run the molecular dynamics on large systems which are inaccessible to DFT, and then investigate properties that we're interested in. To demonstrate the efficiency of the MGP force field, we compared different methods including the density functional theory, GP regression, mapped GP implemented both in Python and high-efficiency C code in LAMMPS, with or without the uncertainties and with one empirical interatomic potential, the bound order potential. As you can see from the figure in the left, the Gaussian process force field reaches 10 to the 4th speedup compared to the density functional theory, while the MGP gives at least 2 orders of magnitude faster than the Gaussian process. What's even more remarkable is the high performance MGP code of the LAMMPS force field reaches speed comparable of the empirical potential. In addition, from the right figure, we can see that the MGP scales linearly with the system size and can run simulation for up to 1 million atoms. Since the MGP is trained with a wider range of temperature compared to the empirical potentials, this fact indicates that this method is very promising to be used to investigate the complex physical processes. Here, for the Stanene system, we train on 32 atoms and 200 atoms with the DFT forces. And in the figure A, we show that the uncertainty prediction identifies the crystal to liquid transition process by the drastic increase. And figure C in the right shows that the uncertainty predicted by our model can identify the defect inside of this configuration. So, guided by the uncertainty quantification, our model collects more and more data that it is not familiar with. And you can see from figure B at the bottom that the error of our model gradually decreases as more training data are collected in 3 consecutive active learning loops. After obtaining a good force field, we can use it to investigate the melting behavior of the Stanene system. Here in the animation, we show that the 10,000 atoms at 500 Kelvin melt from a monolayer to a large droplet. And we also investigate the radial distribution function of the liquid configurations. From the bottom plot, it is shown that the radial distribution predicted in our large-scale molecular dynamics matches very well with the ab initio molecular dynamics results of the liquid TIM from the density functional theory. And finally, we investigate the lower temperature behavior of the freestanding Stanene. In this animation, we show a molecular dynamics simulation at 200 Kelvin. Surprisingly, we find that there's the 2-dimension to 3-dimension BCC lattice transition happening in the Stanene system. So this indicates the metastability of the freestanding Stanene, and this also indicates that the Stanene monolayer indeed has to be grown on a substrate, as a number of experimental papers have reported. So to briefly summarize, we developed the mapped Gaussian process, which accelerates the Gaussian process regression using the fast interpolation approach. Therefore, high accuracy and high efficiency are obtained. Then we trained and used the force field to run large-scale simulation on the Stanene system and revealed its 2D to 3D phase transition. And just as we saw, there is the metastability of this system. So definitely the next step of this project is to investigate the behavior and stability of Stanene monolayer on the top of the substrate. We are also developing acceleration and higher descriptive power of this method. And finally, I'd like to thank my co-authors and the funding resources, and thanks for your attention.